Welcome back to Tokenization from Scratch. In the last episode, we saw why characters and words both fail us. Today we build the algorithm that fixes it, byte pair encoding. By the end of this video you'll have written the training loop yourself, in plain Python, and watched a vocabulary of subwords grow out of nothing but raw bytes. Quick recap of episode 1. A tokenizer only has to do two things: encode text into integer IDs and decode them back. Characters never hit an unknown token but make sequences painfully long. Words keep sequences short but blow up the vocabulary. Subwords give us the best of both, and byte pair encoding is the algorithm that discovers those subword pieces automatically from data. Here's the whole idea in 4 lines. We start with the smallest tokens. There are the raw bytes. We scan for the pair of neighboring tokens that appears most often. We fuse that pair into one new token, give it a fresh ID, and repeat. Do that enough times and frequent chunks like low and low become single tokens, while rare text still survives as its byte pieces. That's it, counting and merging. Let's make that concrete. First we count every adjacent pair in the sequence. Then we pick the single most frequent one. Here the pair LO wins with 3 occurrences. Finally we replace every LO in the sequence with one new token, ID 256. The sequence just got shorter, and our vocabulary just gained a useful subword. One merge done. Now we do it again and again. Our first building block counts pairs. The trick is zip of IDs with IDs shifted by 1, that hands us every neighboring pair in the list. For each pair we bump a counter in a dictionary. The keys are tuples like the pair L, O, and the values are how many times that pair shows up. Simple, but it's the heartbeat of the whole algorithm. The second building block does the merging. We walk the list with an index. Whenever the current token and the next one match our target pair, we append the single new ID and jump the index forward by 2. Otherwise we copy the token across and step forward by 1. The careful bit is that bounce check, so we never read past the end of the list. The result is a shorter sequence with the pair fused. Now our running example. We'll train on the tiny corpus low lower lowest newer new, which shares lots of overlapping pieces. We encode it to UTF-8 bytes and turn those into a plain list of integers. That gives us a starting vocabulary of exactly 256 tokens, 1 per possible byte, and crucially, nothing is ever out of vocabulary, because every character is some sequence of bytes. Running get_stats on our corpus, here are the winners. The pairs LO, OW, and WE each appear 3 times, no surprise, since low shows up again and again. Notice the IDs are just byte values. 108 is lowercase l, 111 is O, and 32 is a space. There's a tie at 3, so we'll simply take the first maximum. That decision is our very first merge. Now we tie it together. We choose a target vocabulary size, here to 64, which is the 256 base bytes plus 8 merges. Each pass through the loop counts the pairs, picks the most frequent one with max, mints the next ID, merges it into the sequence, and records the pair in our merges dictionary. That merges dictionary is the entire learned model, the recipe for rebuilding these tokens later. And here's the payoff. Watch how merges build on each other. Merge 1 fuses L and O into token 256. Merge 2 then fuses 256 with W, So 256 plus W just became low as token 257. By merge 4 we've grown low, and merges 5 through 7 assemble new. The algorithm is literally discovering the words in our corpus, bottom up, from raw bytes. Each new token is a Lego brick built from earlier bricks. Step back and see what we built. 8 merges compressed our 26-byte sequence down to 9 tokens. The frequent stuff got shorter. The new tokens stack on top of each other, so low is built from low, which is built from L and O. And the order of the merges matters enormously. It's the exact recipe we'll replay to tokenize brand new text. Scale this up to millions of bytes and tens of thousands of merges, and those tokens become the familiar subwords like ing, tie-in, and the. Let's recap. We wrote get_stats to count adjacent pairs and merge to fuse a pair into a new token. The training loop just repeats that count, pick the top pair, merge, record until we hit our target vocabulary size. The output is the merges dictionary, an ordered recipe that is our trained tokenizer. In the next episode we'll put it to work, replaying those merges to encode text the model has never seen and decoding the IDs back to the original string, losslessly. See you there.